Okay, hi everyone. I would like to welcome you to my presentation about enabling secure and scalable firmware update over the air over LoRaWAN. So let's first a little introduction about me. I'm Thomas Brunner. I'm head of software at Miromico. I oversee various firmware and software projects, mainly in the embedded space. Miromico is an established OEM and design house, right based in Zürich, Switzerland. At Miromico, we offer various engineering services like hardware design, software development, consulting, and we also help our customers with the production of their electronic devices. We also developed a small amount of our own products, mainly LP1 sensors and gateways for the most common RF technologies. But now let's get to the main topic, the firmware update over the air. In most other industries, automatic software updates are the norm. For example, on your smartphone, you can update an app with one click, desktop applications get updated in the background, and even your smart TV keeps asking you to update the firmware. This has, of course, a lot of advantages. You can provide new features after the launch of the product, you can fix bugs even after the production of the device, and of course, you can improve the security once a vulnerability is discovered. In IoT, however, the situation looks a little bit different. It is largely deploy and forget, which means that millions of devices are left unmanaged. In the best case, this leaves the customer with outdated and buggy devices. In the worst case, the customer has real security vulnerabilities at hand. Another strong motivation to use FUOTA in your projects is the EU Cyber Resilience Act. The EU Cyber Resilience Act sets up guidelines and rules for digital products. This is, of course, also mandatory in the future to get the CE mark on your devices. The EU Cyber Resilience Act ensures that the devices are secure, updated, and that the vulnerabilities are managed. For our special case in the IoT world, I think the most important topics are the secure lifecycle management and also the mandatory update mechanisms. As you might have guessed, FUOTA comes in handy for that, as we are more in compliance with CRA if we have FUOTA embedded into our devices. Now, why is FUOTA not everywhere in IoT already? There are certain challenges that we need to address to implement FUOTA successfully. They are mainly the following. So on IoT devices, most of the time we have limited power resources. We have small batteries or supercaps, which we have to manage the energy carefully. We also have the narrow data bandwidth because of the LoRaWAN protocol. We have duty cycle restrictions. We have unreliable connectivity. And of course, if we want to scale up, we reach certain challenges. Okay, because not everyone's a FUOTA or LoRaWAN expert in this room probably, let me give you a short introduction how FUOTA works on LoRaWAN. So in the beginning, the device is just in its normal operating mode. It measures temperature, humidity, air quality, maybe GPS location, and sends it in regular intervals to the application server. Once we decide that we want to do a firmware update over the air, we have to configure the device. That means we have to do a time synchronization, we have to set up the fragmentation session, and we also configure the multicast group, which is later used for the FUOTA. So FUOTA on LoRaWAN is time-based. So we set a certain time at which the LoRaWAN update starts, and at this timestamp, the device switches from its normal operating mode to class C, which means it is receiving packets continuously. At the same time that the device switches over to continuous reception, the gateway starts sending all the required data packages for the firmware update via the multicast group to a lot of devices simultaneously. Once the device has received enough packages to rebuild the whole image, it verifies and checks the image, and if everything is a match, it changes to the bootloader and updates the application firmware on the device. After this, the device can go back to its normal operating mode and do whatever it was meant to do. Now, these were a lot of software aspects that need to be handled. Fortunately for us, the LoRa Alliance has set up some guidelines and specifications for that. The building blocks that are needed to perform a FUOTA on a LoRaWAN device are the following: the application layer clock synchronization, the fragmented data block support, remote multicast setup, firmware management protocol, and the multi-access protocol. Another important point to mention is that the LoRaWAN FUOTA happens in the application layer, so no special network server should be needed. Okay, let's tackle the first challenge, the duty cycle and the narrow data bandwidth. Of course, if we have thousands of devices in the field and we want to send a firmware update to all of them, we overload the channel. This could cause interference and may be illegal in certain areas. The solution for that is multicast downlinks. In contrary to the normal downlinks, which are only sent from the gateway to one device, multicast downlinks can reach all the devices that are in the same multicast group. It is, of course, still secure via key management and all the messages are encrypted. And the best thing is the whole multicast session can be set up remotely. So you don't need to worry about it when you roll out the device. Additional measures that can be taken to reduce the airtime are to reduce the file size, of course, because then the data that needs to be sent is smaller, or to improve the connectivity, because the different spreading factors take different airtime. The next challenge is the power consumption. Our normal IoT devices or LoRaWAN devices use anywhere between 1 to 5 microamps in deep sleep or when idling. During Class C, when the device is receiving packets continuously, this number goes up to 5 to 10 milliamps, which is a whole magnitude higher. The update duration depends heavily on the file size and the connectivity. In the worst case, it can take up to hours. Of course, as you may have guessed, this heavily reduces the battery lifetime of a device. Solutions for that are, for one, energy harvesting. In the most recent iterations of our devices, we have introduced energy harvesting. Like that, we can perform a power-hungry firmware update over the air, and after everything is done and the firmware is updated, we can refill or recharge our batteries with energy harvesting, for example, a thermoelectric generator. Of course, I will repeat myself here a little bit in the slides. Also important to minimize the file size and to optimize the connectivity, which could be through clever RF design or antenna selection. The next challenge is the data bandwidth and the unreliable connectivity. A normal LoRaWAN device maybe sends a couple hundred bytes per hour to the gateway. If we think of a firmware image that needs to be sent to the device, this could easily be in the space of 50 kilobytes. So as you see, this is a whole other region. Because of that, we cannot use the normal downlinks to just send the whole firmware image, but we need to split it up in smaller packages. Also, because we are operating in the RF space, data packets always can be lost or corrupted. To tackle that, we use fragmentation. Fragmentation splits up the whole image that we want to send into smaller packages and adds error correction. Because of the error correction, the device can verify and reconstruct the whole image from the single data packages that it received. And like that, we can also tolerate the loss or even corruption of multiple packages. The last challenge that I want to address is the scalability. During recent mass deployments, we noticed some problems or challenges that you cannot see if you're doing FUOTA on your desk or just testing with maybe 10 or 50 devices. The first one is collisions of the multicast downlinks. So if you have a device that is in reach of multiple gateways that are all sending multicast downlinks, those packages will collide. We can tackle that either by very accurately synchronizing the gateways, the time on the gateways, or probably the easier way is to add a random delay on the multicast downlinks of the gateways to avoid collisions. Despite the fact that FUOTA on LoRaWAN is handled on the application layer, we still need a little bit support because we want to use multicast. Without multicast, we cannot do it efficiently or scale up. And unfortunately, we have noticed that not all network providers provide support for multicast downlinks. So careful evaluation of a network provider is recommended. The last point is the FUOTA process is fixed to a spreading factor. So you have to decide before you start the whole process, do you want to send the downlinks on spreading factor 7, 12, or somewhere in between. Because of this, you have to do a heavy compromise, because either you don't reach all your devices if you have, or you have a long airtime and therefore very high power consumption of the FUOTA process. So there, a careful consideration is needed. Of course, you could always improve the connectivity of your devices through hardware design or by deploying more gateways in the needed regions. Because I spoke about reducing the file size so much, I want to give you some pointers what you could do to reduce the file size. The first obvious part is to do a partial update, which means we don't update the whole firmware image on the device, but only a small part of it. This could be either done via a delta update, which means that we compare the new firmware to the firmware that is already running on the device and only send the data blocks that have changed to the device. This, of course, needs a much more complex algorithm, and we need rigorous bookkeeping to keep track of which firmware exactly is already deployed on the device. The second part, or the second method to do a partial update, is to separate the application into multiple sections. In our case, this could be the LoRaWAN stack that stays untouched, that we don't update, so we could only send the application part of the firmware to the device and reduce our file size maybe almost by half. There's also other solutions. One of them would be maybe to use an LR1110 chip, which has the LoRaWAN stack already embedded in it with the modem E firmware. Or, of course, during the coding process, you have to take smart decisions. So this starts with choosing libraries with minimal memory footprint, continues with smart algorithm selection or code design, and it ends with the setup of the right toolchain with the right parameters. Now I've talked a lot about FUOTA, mainly in the LoRaWAN part, but of course, if we want to have a secure update process, we need to have a look at the whole chain, which starts at the device and ends at the customer application. So not only the LoRaWAN part between the device and the gateway needs to be secure, but also the part between the gateway and the server and the customer application. Because of that, we at Miromico have developed a new gateway with security in mind. It is fully CRA compliant, and it is designed with security in mind. It has built-in TPM and root of trust, and it requires proper integration with gateway management solutions. With our partner Gapfruit, we offer best-in-class security and fleet management. So the take-home message for today, FUOTA over LoRaWAN is possible and it can scale up. Security is mandatory and Miromico can deliver it. With FUOTA, you have CRA readiness built into your devices, and we at Miromico are your perfect partner for IoT lifecycle management. Thank you very much for your attention, and don't forget to visit us at booth A2.